database transactions. And database systems, like I mentioned before, there are multiple users using the system at the same time. And the database itself is not necessarily stored on a single storage devices. It could be stored on multiple devices that are spanning across the planet in different data centers. And failures are a constant reality, and it's happening constantly. So the goal is such a system has to still run reliably and give legal results. So, so we're going to talk about how that happens. So again, the definition of a transaction, I mean, so far we've always kind of done queries one after another, but a transaction is actually a group of queries that have to be performed. In fact, we've seen transactions before, even though you were not aware of it, things like constraints, foreign key constraints, and triggers. If you realize that those are multiple queries that are running, so if something happens in one table, it affects something else in another table, and all of them have to happen as a unit. Either if you have a trigger, either all the things happen or none happen. So it's an all or none situation. So when you see out here, either they all happen, and it's like saying, you do a commit. Commit means everything's happened, in which case Q1, Q2, and Q3 have all happened. But suppose that there is some kind of failure. Let's say that something, you go do Q1 and Q2, and then there's a crash out here. So let me just, so there's a crash out here. So let me do commit is a good thing that happens. So I just want to, so commit is always a good. Commit means, this is something that you want should happen. It's, it's not a danger thing, but a crash is bad. So if a crash happens, you do not want that Q1 and Q2 has happened, but not Q3. So if a crash happens, you want the system to roll back to the state it was before. So it should come back to the state. So it rolls back to the state it was before anything happened. So that's the whole idea of atomic, that either it's an all or none situation. So an all means it's a commit, and a none means it's a rollback. So that's what really, so we haven't really spoken about commit or rollback or any of that stuff before this, but essentially you've been doing single queries. All your assignments were all one query that was going through, but in general, a transaction is several queries like Q1, Q2, and so on to Qn. And in MySQL by default, and I'll talk about SQL stuff, and is that by default, every query is a transaction. But if you wanted to run multiple queries as a transaction, you can do that. You can have Q1, Q2, Qn, and at the end, you can do either a commit. That means you want all of them to happen. Or you could do a rollback, in which case you want none of it to happen. So that's the idea of, that's what a transaction is just this set of queries. So the whole idea is that in order for something like this to happen, where you treat multiple queries and they must all happen or none happen. So databases must satisfy a bunch of properties, and these are called the ACID properties. So, and these ACID properties are there so that database transactions, they can all execute, correctly or reliably. So I'm going to look at this acid property. So the first thing is, what does acid really stand for? So the A stands for atomicity. So it's something we've already seen before. The C stands for consistency. The I stands for isolation. And then finally, the D stands for durability. So we're going to look at all four of these. And I have to say that the most important one among those is the isolation. So that's the one on which we're going to be spending a little more time. And I'm going to look at all four of these, and I'll look at them in this following order. I'm going to start with durability, which I think is the easiest one, and then go with atomicity and consistency. These are all actually rather easy. And then the last one I'm going to look at is isolation, which I said is the most, is the one that we'll have to spend a little time on. And, and that's the one where you have many options. So in order for databases to, run concurrently and reliably with, and handle failures, all database systems must satisfy or must be able to implement these acid properties. So we'll start with durability. And this is kind of easy. I've already spoken about it. So all durability is saying is that once you commit the transaction, so once you've gone, so let's say so this is time. And let's say we have user one, and the user one is starting up a transaction. So he starts a transaction out here, a begin transaction out here. And this transaction has the following queries. It has queries Q1. So I'm just picking up Q2 and Q3, and then you have to commit. So transaction finishes only after you press commit. You begin the transaction. So that's the T out here saying, okay, I'm starting my transaction now. And then you end the transaction with a commit or a rollback. You could do either. So the idea here is, suppose you have committed your transaction. You typed in a commit, and it's gone through, it's executed, and the cursor has returned. And let's say at that moment your system crashes. So there is this crash right now. So we have immediately after you typed commit and system came back, there's a big crash. Now, you have taken operating systems, and also you are aware that even though when you write things in file and all, oftentimes they're not really getting written to the hard disk. I mean, all file systems and all, they have the write back caches. And write back caches means they get written to the into the RAM, the cache in the memory, and they get written to the disk later. So the whole idea is that now that I've written a commit and the system crashed immediately after I finish with the commit, how do I know whether this has actually got implemented? Did it get done? Did it not get done? So if you're working with databases, you do not have to worry. It's guaranteed. If the commit has got executed, I mean, which means for you, if you're typing, there's a return, you wrote and the cursors come back, it is return. It doesn't matter whether your system crashes immediately or not, you are guaranteed that the operation has taken place. So, that is so the thing is, the database will guarantee if its durability is there in the database, that Q1, Q2, Q3 are all executed and written, and all the changes are written to stable storage. So you are guaranteed this. And how this is done in the back end is that you have to realize is that whenever you do any of these operations, once you do commit, they are written to log files. And log files are written to stable storage. They're written down to disk, and only after that does your cursor return back. So that's how you you are, kind of guaranteed that the operation has taken place, because that's how databases work. So that's durability. It's kind of easy. So then the next thing we're going to talk about is number 2 is atomic operations. And you already understand this since we've done this many, many times. So again, here, I just want to, the same concept. You have user 1, and we do the same transaction T, and you have Q1, Q1, Q2, Q3, and then you do a commit. Let's say commit. Okay, so now the idea is that before you got to the commit, so let's say that there's a crash out here. So you didn't really get a chance to do the commit, there was a crash. Or let's say a crash happened out here. It could be there or it could be here as a crash. So in all of these cases, it's going to roll back to this. So again, like I mentioned this before, it's all or none. You cannot have partial transactions. So there are no partial transactions. It's all happens. If you go back to the examples that we did in the previous class, where when crashes happen, you can get if this concept wasn't there, you can get inconsistencies that that can affect multiple tables. So anyway, I'll give you a tiny example right now. So this one is, let's look at a small table. We have a table with an attribute A, and it has got 3 elements, 1, 2, and 3 in here. It's a table with just one attribute, okay? And we have 3 elements, 1, 2, and 3. Suppose the transaction is just, so the user's running this transaction. So let's say the transaction is just one query that's saying A is equal to A plus 1. So I'm incrementing A by 1. So suppose this is going to start running right now. So we have A, and so now it's getting implemented. So suppose it becomes 2 and it's getting updated now. Okay, so so while it's getting updated, you have 2, 3. At this point, suppose there's a crash. So you get a crash happens out here. So this got updated and now there's a crash. So only half the table was updated. The first 2 rows were updated, but it didn't get to the 3rd row. So in this case, it is going to roll back to the previous state. So the rollback will happen and you're going to go back to the original table. Only if it commits would you get to this situation where you get A, just 2, 3, and 4. So you're never going to have a situation where half the table has got updated and the other half has not got updated. So this is one of those cases where it's within one table you're getting an attribute level inconsistency. But you can, if crashes happen, you can have inconsistencies. If you didn't have this property of atomic property, let's take that bank example, or actually let's take the airline example that we did in the previous class, where you update the flight table and then you update the reservation table. In that particular case, if there was a crash, it happened, say, after you updated the flight table, but before you did the reservation table, then you have an inconsistency that's going across tables. So it's not just in a single table, but multiple tables. So it's extremely important to have this property where, that everything happens as one unit. And again, like I mentioned in the before, even triggers and constraints we've done before, they all have to happen atomically. So that's another really good example. Okay, so that is the atomic property. Then the next property we're going to look at is consistency, which is actually rather easy. There's nothing really much to that. So consistency it's really all it's saying is that databases, whatever they do, they have to preserve the consistency. And again, it's like in the banking example, if you updated one account and you didn't update the other account, then your database is inconsistent. And again, you shouldn't violate any triggers and constraints. So that's all consistency is really talking about. So triggers or sorry, transactions will preserve consistency. By constraints and triggers. So there's really nothing much to the consistency part. So we're going to get to the key part, which is the isolation part. This is the one that we're going to uh, really talk about. So this is a property that databases really struggle to kind of handle. So, so, so that's the number one property, isolation, or number four property. So isolation really is saying that, databases, there are multiple users using it at any point in time. It's concurrent applications. That's the whole point of having databases. Any point in time, if you look at my courses, there's so many of us using it. Any point in time, the airline database, the banking, there are multiple users using it. So what isolation is really saying is that even though multiple transactions are running, the effect should be as though all of these transactions, even though they're running concurrently, it looks like they are running in a serial order. There's some kind of serializability. So yes, I kind of spoke about it yesterday with the banking example, but I want to go a little more into it. So this is what it really states, is that isolation is that so multiple transactions, or let's say two transactions, that run concurrently should not see each other's intermediate states should not see each other's intermediate states actually, or changes before the transactions complete. So that's really what isolation means, that even though, things are running in reality, they're running concurrently. Um, you shouldn't really be able to see each other's intermediate states, so so isolation is achieved by serializability. So they kind of um, so let's take an example. I mean, I just want to do we did one earlier, but I would just want to show one simple example. Suppose we have the following transactions. We have transaction T1, which has queries Q1, Q2, and Q3 in order. We have transaction TA, which has queries Q1 and Q2. And we have transaction TB, which has queries Q1 dash, Q2 dash, and Q3 dash. Okay, suppose we have these three transactions. So what isolation means is that, or serialization means is that the database will guarantee. So what serialization means is that serial guarantees that. Okay, so let's say that T1 is run by user one. I didn't finish that. So let's say, so I have, so this is user one, and he's running T1. So he runs T1, so which is Q1, Q2, and Q3. And then we have user two, who's running TA and TB. So he runs TA first, so which is Q1, Q2, and then he runs TB, which is Q1 dash, Q2 dash, and Q3 dash. Okay, so we have two different users. One user runs T1 and the other user runs TA and TB in order. So serializability will guarantee that the output, so guarantees that database output looks like. So the output, you can guarantee that it will look like, either it's going to look like T1 followed by TA, TB, or it could be TA, T1, TB, or it'll look like TA, TB, T1. I guess those are the only options, right? Yes. So the database system will guarantee that the output will look like this. But if you look out here, it's not, these two transactions could be running concurrently. So TA and TB can never run concurrently because it's run by the same user. So TA must always come before TB. So that is guaranteed, that TA will, and then you have TB in time. That is guaranteed because it's run by one user. But if you look up here, T1 could run, it could be run at any time. You can't control how two different users at what time they're doing stuff. So all the database is guaranteeing is that whichever way they run, that the output will always look, either in one of these three forms. So, and at the same time, the database, while the database can be executed, the actual execution need not be serializable, but the output should be serializable. So this is important that so I'm going to write this in red, is that the actual execution, and you can see that by looking out here, because the actual execution is running concurrently. So the actual execution may have parallelism. So the actual execution may be running, may be concurrent, but the output or the result is equivalent to some serial order. So this is something that the database is guaranteeing. So, does anyone have any questions? So I'm just going to look at the previous lecture. I just want to open up the last lecture that we did the other day. So if you look at, we did this with a bank example. If you look at the bank example out here, I said that, we had these two. We had user one who was transferring money from account A to account B. So user A, we were taking $10 out of account A and moving it to account B. And user two was just reading the bank balance. And we were starting with $150, $100 in balance A and $100 in account B. And like I mentioned, is that it doesn't, the output should always, these are the only possible orders that the output can have. So the output could either be, so this 150 means that T2 happened first, followed by T1, or it could be T1 happened first and followed by T2. So that's what it means, is that the output should always look like this. It does not mean that this is the only way. Maybe in reality, the reality may not have been like this. The reality might have been like this. So in reality, maybe this is what happened. So we have user one. Was that user one and user one and user two? So we have user one, user two. Maybe this is what happened in reality. You have Q1. I just want to make sure, was it? Yeah, Q1 and Q2. So Q1 happened and then Q2. And maybe out here it was Q1 first at this point. So I'm showing time out here, okay? So, and then let's say we have Q2 and then Q3. So maybe, so if you look at it in reality, maybe this is what's happening in reality. Reality at this point, Q1, balance A, account A. I think I called it. I just want to see what it is. Read X is equal to 100. So let's call it X and Y, or A and B. So at this point, we had 100 out here. A was 100. At this point, after Q1, now A becomes 90. Now at Q2, B becomes 60. So in reality out here, B is equal to 60 because this is happening after. And so when you print out Q3, when you do Q3 out here, it's going to be printing out A is equal to 100 and B is equal to 60, which is incorrect. So the reality may be like this. you know, but the database must always guarantee that when the output comes, it should always appear as T1, T2, or T2, T1. So that is the whole idea. That's why I said it's a bit kind of, the isolation is a little more complicated than any of the other three parts. And I'm going to continue with this in the next class. So do you kind of understand? Do you have any questions? Okay, so if you don't have any questions, I will